today we will discuss a new topic. No? Um, we will discuss about second order linear differential equations. We have discussed all first order, although not really all, no, because the first let's recall for a while everything that we have discussed so far. So recall. So these are the methods that we have used so far in solving a differential equation. The first was when the equation is separable, no? So separable variable. It's actually the easiest to use when we can separate the two variables x and y. We just isolate one variable on one side and the other variable on the other side, and then integrate both sides. No? The second was called a homogeneous. So many homogeneous differential equation. This actually sort of an extension in a way, because this is not a separable equation, but we can find a way to make it separable by introducing a new variable, which is v equal to y over x, no, if you recall. So the third was called an exact equation. Here, this is linear first order, right? So exact equation is linear first order. The next one is almost exact, no? So let's just put it under 3. Almost exact because at first, if we check for exactness, it is not exact, but we can actually find the what we call integrating factor. We can find the integrating factor so that when we multiply that integrating factor times the differential equation, the equation becomes exact. And the integrating factor is equal to, we denote it with mu of x. So it's actually a function which can be solved by raising to power the constant e, and the power is the integral of the partial of m minus the partial of x all over n dx. Or, although we did not have an example of this, mu of y equals e raised to the power nx minus partial of m with respect to y all over m dy. No? But so far, we have used only the integrating factor in terms of x. And the fourth linear equation, linear first order, right? So linear first order differential equation. This is of the form general form dy dx plus y with a coefficient which is a function of x. So we call that p of x multiplied to y equals another function of x, say q of x. P and q are just names, no? You can use other letters. To solve this, we will also use integrating factor. And the integrating factor is solved by, again, raising to power the constant e, and the power is the integral of p of x dx, which is this p of x. No? So we had several examples in the last video. You can review that video, no, for the next quiz. So today we are going to talk about second order, no? So second order second order linear, so second order linear differential equations. The most the most general form of a second order differential equation, so the most general form is when you have second order, right? So it should involve second derivatives. And this may have a coefficient which is a function of x, say p of x, plus the first derivative, so dy dx, times another function of x, say q of x, no? dy dx, plus the function itself, which can also be multiplied with another function of x, say r of x, times the function y. So y dy dx, second derivative of y, no? Equals another function of x, say g of x. But most of the time, this equation is actually difficult to solve, no? So it's difficult to solve. We'll make a note. So note, most of the time, this is very difficult to solve. Now, what is easier to solve is a second order linear differential equations where the coefficients do not contain variables. In other words, they are just constants, no? They are just constants. So when the coefficients are constant, it is easier to solve. So, how does a second order linear differential equation with constant coefficients look like? So, just make the coefficient constant, no? Say a constant A. Oh, by the way, we don't usually use this notation because they're so try tawag lisod isulat. You can also write this as the function p of x y double prime plus the function q of x y prime plus the function r of x y equals another function g of x. So we're going to use this notation because it's easier to write. No? So that means that when the second order linear differential equation has constant coefficients, we can write it this way. So I say a constant A times y double prime plus a constant B times y prime plus a constant C times the function y equals the function g of x. No? The function g of x. But this is that, well, it's easier to solve but not that easy. What is the easiest to solve is when the right side g of x is equal to 0. No? So let's make another note. Easiest to solve when g of x is 0. So the equation would look like this: a double prime plus b y prime plus c times y equals 0. When the right side is 0, the equation is also called a homogeneous. I don't know why they like this name so much. No? Recall that we already have a homogeneous differential equation before, but this is when you let v equal to y over x, right? Here, it is called a homogeneous differential equation when it is second order linear with constant coefficients. The right side is 0. Okay? So, when the right side is not 0, like this, no, it's called a non-homogeneous differential equation. Second order linear differential equation. So take note, it should only be linear. So how do we solve this? So it's actually very easy to solve. Now let's have an example to illustrate. So so it should look like this: a y double prime plus b y prime plus c times y equal to 0. No? Now, let's let's examine this equation. It says that we have a function y which is multiplied to a constant, so it could be a multiple of the same function. If we are to combine that function with its first derivative, when we combine, we mean we add or subtract. So when we combine that function, which can be multiplied by a constant, so a constant multiple of itself, times another constant multiple of its first derivative and a constant multiple of its second derivative, it's now equal to 0. No? So, what is that? How do we combine in algebra? No? Recall in algebra, we combine similar terms. Remember that? Similar terms. In other words, example, can only combine like 2x plus 3x, right? Equals 5x. If you'll have 3x plus 2y, we can no longer combine. The result is just 3x plus 2y. So here, if we can combine, in fact, the result should be 0, then y prime, and y double prime should be similar. Should be similar so that we can combine, right? So what is that function whose derivatives are similar to itself? There's no other. Diba? It is only the function, the exponential function, right? Y. So there is only one function that behaves, that has this characteristic, no, meaning what is this characteristic? Whose derivative is itself, and it is the function e to the x, right? So it is the function y is the function y equals e to the x. But y equals e to the x, x could also have a constant coefficient, no? So like some constant, say r, yr. I don't know, but the book uses the variable r, no? Multiplied to x. So r could be 2, 1/2, -3, no? It is a real number. So y equals e to the rx. So that we can check, no? If we have a function, so y equals e raised to x, which can be multiplied to any constant r, its first derivative, what is y prime? So it's just copy the function, but by chain rule, we multiply this by r. So y prime is r e to the rx. The second derivative, because we're dealing with second order linear differential equations, is copy the coefficient r. The derivative of e to the rx is also e to the rx. By chain rule, we multiply it by another r. So r times r is r squared e to the rx. This is y double prime. This is y prime. So this is y prime. This is y double prime. And this is the function y. So what do we want to do here? We are solving a differential equation, and the solution of a differential equation is a function y, or a function f of x. So in other words, we want to solve this y, no? Which would satisfy the condition that its derivative times a constant plus its second derivative times another constant. When we combine all of them, the result is 0. Okay? So that is what we want. So in other words, we want to combine all this, no? Y prime, y double prime. So when we multiply, we will get, or when we check, so we check. So the equation is what color are, let's try blue. So the equation is A y double prime plus B y prime plus C times y equals 0. Y is e to the rx, but we'll start with y double prime, no? So A times y double prime, which is r squared e to the rx plus b times y prime r e to the rx plus c times y, which is e to the rx equals 0. So, note that e raised to r times x, e raised to r times x, e raised to r times x is common to all three terms. So we can factor out, no? So, well, we can actually write this as a r squared e r to the x plus b r e r x plus c e r x equals 0. So factoring out the common factor e raised to r times x, so we'll have e raised to r times x times, we are left with a r squared plus b r plus c equal to 0. So if you recall in your algebra, if we have a product a times b is equal to 0, what does this mean? This means that b should be equal to 0, right? So that when we multiply a times 0, the result is 0. Or if b is not 0, then we have to set a to 0 so that 0 times any b will result to 0. But it could also be that both a and b are 0, so that 0 times 0 is 0, right? In other words, it's either this is equal to 0 or this is equal to 0. But e raised to rx, so e raised to rx is always positive. Why is it always positive? So this is always positive. Because if we graph it, no, look at the graph of y equals e to the x. It can have any coefficient. The graph, so when x is 0, what is e to the 0? 1. So it passes through 1. So when x is 0, when x is 0, when x is 0, y is 1. Here, when x is 0, y is 1. When x x is 1, y is e. So, like that. No? Okay, it's exponential. So, when you have an exponent, the function will only grow without limit. But what happens when x is negative? When x is negative, so y equals 1 over e to the x. So, it's less than 1, di ba? 1 divided by any number that's not fraction is smaller than 1. So, the graph looks like this, no? And it is asymptotic to the x-axis. Like that. So, as you can see, y can never be 0. Y can never be 0 because it will not touch the y-axis. In fact, let's look at the graph, no, of an exponential function. So, we have here a graphing up. So, let's graph y equals e raised to x. Raised to x. Ano ba yan? Raised to x. So, look at the graph. No? So it looks like it touches x, but it actually does not, no? It is asymptotic. It can never have a 0 value. Okay? So the graph looks like this. Okay, so it crosses y at 1. So what if x has a coefficient, say 10? So as you can see, the graph does not change in a way that the behavior is the same. It crosses the y-axis once and it just goes up without bound. And when x is negative, it's less than it's less than 1, no? So what happens when it's negative? -2. So as you can see, it is just flipped, no? But still it does not touch the x-axis. So the point is that y equals e to the x, where x can have a positive or negative coefficient. Y can never be 0, right? So y can never be 0. So if e raised to rx is always positive and cannot be 0, then we are forced to set the second factor to 0. Diba? So then, maybe let's use another color. So then, a r squared plus b r plus c is equal to 0. So, if you look at this, our variable is r, right? Because a, b, and c are just constants. R is something that we do not know, right? This is just a quadratic equation, right? So if given any quadratic equation, you can always solve it, right? By using the quadratic formula. So this equation, ar squared plus br plus c equals 0 is what we call the characteristic equation. So characteristic equation, or sometimes it is called auxiliary equation. What's the spelling of auxiliary? Only 1L or 2L? So auxiliary. Only 1L. Okay. So There's only one L. So, auxiliary equation. Auxiliary equation. Okay. So, this is how we solve a second order linear homogeneous differential equation with constant coefficients. So, let's have a specific example, no? So that we can check out how easy it is to find the solution. It's the easiest compared to the previous ones that we have already discussed. So, example, we have, let's try something that is easy to solve. Say we have 4y double prime minus 5y prime minus 6y equals 0. Note that it can also be written as 4 y second derivative of y minus 5 first derivative of y minus 6y equals 0. No? But we prefer this notation. It's clean and concise. So, what do we do first? We are going to solve for the arbitrary auxiliary equation or the characteristic equation. What is that? Is just a r squared plus br plus c. So, what is a? 4. What is b? Negative 5. What is c? Negative 6. So, the characteristic equation is what? It's ar squared. So let's write it here. Car equation ar squared plus br plus c equals 0. So this would be 4r squared minus 5r minus 6 equals 0. Alright, so we are going to solve for r. 4 times 6 is 24. Are there factors of 24 that is equal to 5 negative? 5, 8, and 3. So it is factorable. So what are the factors? Factors are what? 4. 4r times r. Maybe it's 2r times 2r, no? 6 could be 2 times 3. So if this is a 3, 2, it's negative. So it should be plus and minus. So minus 3 plus 8. Oh, it's check except for the sign. So this should be plus. This should be negative. So positive 3r, negative 8r is negative 5r, which is that one. So equating to 0, so 4r plus 3 equal to 0, r minus 2 equal to 0, 4r equals negative 3, r equals negative 3/4. Here, r equals 2. So what are we going to do with r? This is the solution. Y equals e to the rx, but there are two r's. So this is r1, this is r2, no? So one solution would be y, it's y equals e to the rx, right? So y equals e to the r, which is negative 3/4 x. So y equals e to the rx. The other, so this is solution 1. The other is y2 e to the r2x. So r2 is 2, so 2x, no? So one property for differential equations is that the sum of two solutions is also a solution. We can actually show it, but it would take time, no? So we'll just accept it as fact that a solution, so one property is y solution is equal to y1 solution plus y2 solution plus yn solution. If it happens that there are several solutions, no, the sum of those solutions is also a solution. Therefore, the solution to this equation should be, so the general solution is y equals this, so y1 plus y2. So y1 is e to the negative 3/4 x plus e to the 2x. No? Now, let's check. Let's check, no? So that we will see if these really are say tawag solutions. No, they're really solutions. So let's check. Is this a solution? So check. Let's use block. Check. So 4. Oh, we need to differentiate. So y equals e to the negative 3/4 x. What's y prime? Negative 3/4 e to the negative 3/4 x. Y double prime is times another 3/4 is positive 9/16 e to the negative 3/4 x. So 4 times, so check. So 4 times 9/16 e to the negative 3/4 x minus 5 negative 3/4 e to the negative 3/4 x minus 6 e to the negative 3/4 x should be equal to 0. So we can cancel. So this is 4. So we have 9/4 e to the negative 3/4 x minus is plus 15/4 e to the negative 3/4 x minus 6 e to the negative 3/4 x is equal to 0. What is what is 9/4 plus let me turn off the notification. Okay, what is 9/4 plus 15/4 is equal to, what's 9 plus 15? 24/4. What's 24 divided 4? 6. So this is just 6 e to the negative 3/4 minus 6 e to the negative 3/4 x is equal to 0. So yes, e to the negative 3/4 x is, y equals e to the negative 3/4 x is a solution. What about the second y, e to the 2x? So let's post this. We're done with this. So we'll just maybe So let's try to check out y equals e to the 2x, y prime is 2e to the 2x, y double prime is 4e to the 2x. So let's check out 4 y double prime, so 4e to the 2x minus 5 2e to the 2x minus 6 e to the 2x, is it equal to 0? So 4 times 4 is 16 e to the 2x minus 5 times 2, 10 e to the 2x minus 6 e to the 2x, is it equal to 0? So we have 16 e to the 2x, minus 10 minus 6 is minus 16 e to the 2x equals 0. As you can see, 0 equals 0. So the second solution is also a solution. But to make the solution more general, so another characteristic or property is if you have if y is a solution, then a multiple of y, say cy, is also a solution. So as I've said, we can actually show that, but let's just accept it as fact. Therefore, the general solution, the most general solution, so it's so go both, so most general solution is y equals a constant c e to the r1x, but there's a second, so c2e to the r2x. So this is the most general solution, like that. Okay, so let's have another example. Say we have example 2. Example 2. So say 1 y double prime plus 3 y prime minus 10 y equals 0. So what do we do first? We first find the characteristic equation. Let's first identify our a, b, and c. So a equals 1, b equals 3, c equals negative 10. Negative 10. So the characteristic equation is what? R1r square plus 3r plus minus 10 equal to 0. So this is factorable. Factors are r plus 5, r minus 2 equals 0. Solving for r negative 5, r equals 2. Therefore, the equation, the solution is, so r1, r2, the solution is y equals c1e to the r1x plus c2e to the r2x. So it's y equals c1 e to the negative 5x plus c2 e to the 2x. So just like that, and that is the solution. So we will also solve IVP, with initial conditions, meaning we will solve for the particular solutions. So how do we solve for particular solutions given second order linear differential equations with constant coefficients which are homogeneous? So maybe let's have one more example, no? So example 3. This time let's have what? 3, 8, 24. So 3 y double prime plus 2 y prime minus 8y minus 8y equals 0. So characteristic equation, so a equals 3, b equals 2, c equals negative 8. So it's 3r squared plus 2r minus 8 equals 0. What are the factors? 3r, r, 4 and 8. 4 and 2. So 4 and 2. Plus and minus. So plus and minus. Negative 4r, positive 6r, positive 2r. So correct. So R1 is positive 4/3, R2 is negative 2. So the solution is y equals C1 e to the 4/3 x plus C2 e to the negative 2x. Alright, so what if this is an IVP? So for example, we have let's solve IVP much later. One more example where the characteristic equation is non-factorable. So example 4, right? Example 4, say we have y double prime minus 6y prime minus 2y equals 0. So a equals 1, b equals negative 6, c equals negative 2. Very obvious that, well, the characteristic equation is r squared minus 6r minus 2 equals 0. It's obvious that this is non-factorable, so we can solve for r by quadratic formula. So solve for r by quadratic formula. So r equals negative b plus minus the square root of b squared minus 4ac all over 2a. So it's negative of negative 6 plus minus the square root of negative 6 square minus 4 times 8 times c all over 2a, which is 1. So it's equal to 6 plus minus the square root of 36 plus, what's that? 4 times 3, 12, all over 2. So this is 6 plus minus square. What's 36 plus 12? Oh, 36 plus 2. 8 lang. 8. What's 36 plus 8? 44? 44 all over 2. So we have 6 plus minus, what's 44? 4 times 11. 2 square root of 11 all over 2. So 2 is common. So we can factor out 2. We're left with 3 plus minus square root of 11. So R1 is 3 plus square root of 11. R2 is 3 minus square root of 11. So therefore, the solution, general solution, is y equals C1 e to the R1x, so 3 plus square root of 11x plus C2 e to the 3 minus square root of 11 x. Okay. Oh, it's already 50 minutes. So it's getting longer. So I'll better post this.